Yeah, I'm Andrew. I'm one of the team at Technia, and during this talk, I'm going to be the design engineer.
Hi, I'm Ollie Brayshaw. I'm one of the simulation engineers at Technia. I mainly work on the support desk, and I'm going to be the simulation expert in this episode. So in this episode, we're going to be talking about assemblies and how to simplify them.
So the model I've got here is the Hamatro spreader I've been working on. It's the jaws of life that are often used by the fire brigade. It's a very chunky bit of kit, and it's used in emergency situations and to help open up damaged and crumpled cars and large bits of debris in natural disasters.
Oh, that's really interesting. So what did you want help with exactly?
So I need to make sure that these components aren't going to fail. A physical test will take a long time, and it's going to be really expensive. So I'd like to simulate it if we can. I'm not too sure how to go about doing that effectively, though. I want reliable results, and I need them quickly. Can I simplify this in simulation?
Yeah, of course. It depends on what you're trying to simulate and the outcomes you want it, but we definitely can, yeah.
Right, great. I've got a few questions. They focus on different aspects of the design when it's being used.
Yep. Okay, great. Well, in simulation, those questions are called load cases. And depending on the simulation, it might be the case that we only need to consider one of the parts in assembly to get an accurate representation. Or it might be that we can model multiple parts in order to get the right behavior, just on that one part of interest. Reducing the number of parts will reduce the runtime of the model, but it can affect accuracy. So it's up to the engineer to decide when it's appropriate to make these assumptions and approximations, but I can help you with that. So why don't we go through your load cases now?
Okay, that makes sense. An area of interest is the arm and whether they're going to be within the specified deflection and deformation limits.
Right. So if the loads are known to us, we can simulate the arm individually just by using boundary conditions and constraints. So for the arm, we could use a constraint to represent the pin, which the arm is rotating about. This would fix the nodes on the inner surface of that hole in the X, Y, and Z planes, but allow for axial rotation, just like a real pin. We can then apply a force or a displacement with a connector to represent the short link, which is transferring the load from the piston to the arm. Or we could use a coupling or constraint like the other pin, but apply loads to that. So all of these methods will reduce the complexity and the computational demand.
So, oh, okay, yeah, that makes sense. We know the maximum force the hydraulics produce from the manufacturer, so we could use those as the boundary conditions.
Yeah, absolutely. So yeah, we could use those and apply those forces to the places we just mentioned, and then we could fix the top of the arm to enforce the bending. That would give us the worst case scenario and allow us to observe the part's stiffness and how it would deform. I'd also remove the black polymer tips, as they won't impart any significant stiffness on the model, and all they're doing is just increasing the complexity in this case.
If I need to redesign some features, is it going to be easy to test it again?
Yeah, so it's really easy. You can edit the part in the cloud, and it will update the finite element model in the simulation app. And then provided the defined surfaces and holes are in the same place, the loads, boundary conditions, and any constraints will update automatically. You can then rerun the simulation without too much editing.
Oh, brilliant. What about the parts the jaws are pushing against?
Yeah, so there's a few options for modeling the components the arms are pushing against. We can model them as a boundary condition, as we just did, because they weren't of interest in that case. Or we could model them as a block, which we can push against and deform. But we would have to apply a boundary condition to that block to basically keep it still and allow the arm to push against it. But with the introduction of multiple parts, we now need to think about contact. So we need to define parameters like friction. This nonlinearity makes the model slightly more complicated, as it will cause sudden changes in stiffness, which will make the model harder to converge. But I can help you set that up later.
Okay, so if we must use multiple parts, how can we simplify other aspects for the reduced runtime?
Yeah, an easy way to reduce the runtime and still get accurate results would be to apply symmetry. So basically, we'd only model half the geometry. This works well in this case because we can just simulate one of the arm and all of its accompanying parts and constraints. Another way would be to make some parts rigid. This is reasonable if we have concluded that they are within the safety factor or a max allowable stress. Or in the case of the arms, they'll be much stiffer than whatever we're bending. So it's a reasonable assumption there.
Okay, so what do you mean by make them rigid?
So making them rigid just means they're non-deformable. So no stresses or strains will be calculated on those elements. It makes them much more computationally efficient. So they'll purely transfer loads from the RAM through the components to the block of material. This is an appropriate way of including parts which affect the behavior of the model but aren't likely to fail.
Another potential failure point are the short links. How can we simulate this?
Yeah, the short links would be best simulated using 3D solids. This would allow us to best capture the bending and buckling modes, but we could also model them as 2D shells to reduce the number of elements, and it would still be accurate in this case. We then simply apply boundary conditions to each of the holes to represent loads going through them. If they weren't of interest, we could substitute them for a 1D element or a connector, then they would simply transfer the loads.
Okay, so the bolts joining the arms and the yoke are also rated from the manufacturer, but we require a safety factor as part of the specification. Can we handle that?
Yeah, absolutely. We could model the bolts as simple cylinders. So we'd neglect the thread and include a bolt preload on a created surface in the middle of the bolt. The surrounding holes could then be rigid parts or constraints just representing the holes. We then do hand calculations on these, as we will know the stresses going through them from other areas. You could also model them as a 1D element with a profile attached to it. This would still allow us to get some values, and they would be pretty accurate in this case. In 3D experience, you could also model virtual bolts or pins, which create representations of the connection without actually adding any elements.
Okay, brilliant. I really appreciate that. I feel much more confident about simplifying the assembly now.
Good. Yeah, I'm happy to help. Don't hesitate to get in contact if you need any more advice or have any issues. The sooner we start simulating in the design process, the more effective the design will be and the cheaper it becomes.
Brill. Thanks, Ollie.
All right, no worries.